Hello everyone, my name is Artur. I'll be presenting work done jointly with Sid Banerjee and Iyer from Cornell. The subject of this talk is repeated allocation without money. There are many practical examples of that. Think about students of university competing for reserving a room on a daily basis, or a charity that needs to decide whom to allocate resources, say, every month. And the common feature is that because agents in the game are already in some way entitled to the resource, it would not be ethical to use money. So we have to be able to efficiently allocate resources without it. And so I'll start with a simple example that might be useful to keep in mind throughout the talk. Suppose you have two players who are competing for a single parking spot daily, and the value they have for this parking spot varies, and we model that with drawing their values for the spot every day independently. Our ideal outcome would be on every day to allocate to whichever agents wants the spot the most. And the problem, obviously, that we face is that without money, it is not at all obvious how to ensure incentives. The setting we're going to be considering is much more general. We have n agents and t time periods, and in each period, every agent would draw their type, and then the mechanism would be to choose some allocation, and every agent has some arbitrary utility function that depends on the type and the allocation. And finally, as I mentioned, use of money is not permitted. In this setting, we are going to be concerned with welfare, which is the sum of all agents' utilities through all time periods. And one benchmark you can think of is first best welfare, meaning the welfare would be able to get were we to know all the types of all the agents. The problem is that we know that even in monitoring mechanism design, this might not be tractable. Optimizing welfare it is. So a more reasonable benchmark to adopt is to say, well, suppose you give me a mechanism that makes use of monetary payments. How well does it do? Can we match that? So there's been some previous work on repeated allocation without money. It's been in a less general setting, namely for the case of one item. There's been a result by Guo and Konitzer that shows an incentive-compatible mechanism that guarantees 85% of optimal welfare. And a very recent and, in my opinion, surprising result of Balsera et al. Is vanishing inefficiency. I see mechanism with vanishing inefficiency as discounting goes to 1. One problem with those mechanisms is because ensuring incentives in a setting where future valuations are unknown is hard, the mechanisms turn out to be really complicated too. And I mean that in 2 ways. First, it may not be very easy for actual people to grasp how those mechanisms work. And secondly, in theoretical reasoning, it may not be, it's not at all obvious how to generalize those mechanisms to other settings. And so one might ask, well, maybe it is possible to trade off the strong incentive properties and go with something approximate, and instead, in return, gain better, more general results for a simpler mechanism. And our previous work has been an initial effort in this. So again, for the case of one item, we demonstrated an approximately incentive-compatible mechanism that has vanishing inefficiency. And this was for finite horizon setting. And the theme of this work is also this, trading off incentive guarantees for a much general, simple result. So what exactly do I mean by approximate IC? I'm going to use this following definition. Mechanism is alpha beta approximate if first an agent can gain at most alpha t by deviating from truthful reporting, and at most beta t welfare is lost as compared to that benchmark that I described. And our objective would be to find a mechanism with both loss in incentives and loss in welfare sublinear. And I'm now going to switch to describe a mechanism that satisfies exactly that. So the approach that we take in constructing such a mechanism is a reduction from a given monetary mechanism to a non-monetary one. And one simple idea to do that is the following. You issue some artificial credits. You endow agents with those artificial credits, and you ask them to play a monitoring mechanism using artificial credits for payments. Now, for it to be better defined, we need to basically answer two questions: how much credits to give, and how do we deal with people who run out of credits? And this is our mechanism that basically answers those two questions. So in terms of allocations, let CS be the per period expected payment in the monitoring mechanism. Under truthfulness, we allocate CS times the number of rounds, which is expected expenditure during T periods, and then a little more. So our total budget is T, CS, 1 plus delta, and I'll talk about delta later on. And then how do we deal with bankruptcies? Well, as soon as some agent runs out of money, we're going to replace that agent with their simulated doppelganger. And what do I mean by that? As soon as the budget drops below 0, we are going to, from then on, disregard that agent's reports, replace them with simulated reports from the prior, and we're not going to allocate anything to that agent. Now, for this mechanism to work, we need a couple of assumptions. First one is about the allocation setting we're working in. Namely, for the last step, devoiding agents of allocations, we need to be able to basically not allocate to one agent without touching other agents. And to formally state that, we say that for any allocation X and agent S, there exists another allocation that basically preserves all the other agents' utilities, but sets this one agent's utility to 0. For example, not allocating any items to this agent and keeping other allocations similar. And this assumption covers the setting of combinatorial auctions, of shared services, but it does not cover bilateral trade and public projects. Another point is that we need to make some assumptions about our monitoring mechanism. Not surprisingly, we need it to have some incentive properties. Namely, we would require it to be Bayesian incentive compatible. We also need payments to be bounded, which in turn implies that we can always scale them by a constant and ensure that all payments are positive. And somewhat more restrictively, we need there in the mechanism to exist a payment that would guarantee you 0 payment. For example, in second price auction, you can always bid 0 and thus guarantee yourself to not pay anything. With these assumptions in mind, we can state our main result. So on the top is the definition of alpha beta approximate mechanism, just to remind you. And our main theorem is for a mechanism described with the budget surpluses set correctly, the mechanism achieves vanishing alpha and beta, meaning sublinear loss in both incentives and welfare. Another result is that, remember when we set budgets, we used expected payments for all the agents in the monitoring mechanism, but computing expectations may not be tractable. So we show that if you set those budgets using examples over T-type samples, you can achieve the same guarantees of alpha and beta, and thus the amount of computation required to run T periods is twice that of running the monitoring mechanism. Finally, one might not find it satisfying to go with approximate IC constraint and ask, well, what happens in the equilibrium, the actual equilibrium of this game? And the problem is that it's a very complicated question to answer. In our paper, we provide a solution to this for one specific case of having 2 agents and using I'll-pay VCG for the monitoring mechanism we input into our reduction. And for that case, we show that any equilibria is almost efficient. I am now going to switch to try and explain why is it that this mechanism works and how do we go about proving it.
What is all-pay VCG?
So we take VCG payments with Clark pivot rule, and then we basically take expectations of payments.
Okay.
So you first pay, then
the
you...
expected externality mechanism.
You could name it that.
Excuse me, could you put the mic onto your collar because
Do I click it?
Anyways, the proof technique. I wanted to start with giving you some intuition for how does the artificial currency capture the incentive properties or approximately capture incentive properties of real money. And to do that, I'm going to simplify matters a little bit. So assume that some agent S in advance knows all the future types for both him and other players. And moreover, suppose the monitoring mechanism that we use is dominant strategy and sense compatible, which is stronger. For this setting, let's formulate what is the optimal strategy for agent S. Let US and CS be the payments, utilities and payments in the monitoring mechanism. Then problem of finding optimal strategy in the artificial currency setting would be maximizing your utility subject to budget constraint, whereas problem of finding optimal strategy in monetary setting is maximizing quasi-linear utility. And what we know about the monetary setting is that because the mechanism is DSIC, the optimal strategy is truthfulness. Now, how can we use this to reason about the problem on the left? So suppose the budget that we set on the left is actually the budget that you need to play truthfully, plus a little bit more, plus epsilon. Can we reason about how much an agent can gain by deviating from truthfulness in this case? I'm going to argue that you cannot gain more than epsilon from having epsilon surplus. And the argument goes as follows. Suppose the optimal strategy is not truthfulness, and the optimal strategy on the setting on the left. And the utility that you gain is in fact better than truthfulness by more than epsilon. Well, then you can just take this strategy, there's the optimal strategy, and play it in the monetary setting. You're going to gain more than epsilon utility, more compared to truthfulness, and you're only going to pay epsilon more, which means your quasi-linear utility is going to be better in the monetary setting, which contradicts the fact that the mechanism is DSIC. So essentially what this demonstrates is a sensitivity result that is asymmetrical. So we know that having epsilon more budget than truthfulness guarantees to yield no more than epsilon utility. Importantly, we cannot say the same thing about the opposite, about not having enough money, so having epsilon less than you need to play truthfully. And we'd have to go around this asymmetry. And this creates the following tension. On one hand, we would like it to be with high probability that agent has more credits than they need. And for that, we need this delta in budget to be large. Basically, to guarantee agent to not run out of money if he's playing truthfully. And then, on the other hand, we need delta to be small because we know that having epsilon more budget than you need results in epsilon more utility, which means gains from deviations. And our argument essentially comes down to trading off between those two problems, and a particular choice of delta works. Now, of course, the reasoning that I used was for known types and also using DSIC mechanism and relaxing those assumptions and rigorously treating the uncertainty that relates to random types needs a more formal framework. And I'm just going to say a few words about the framework that we use for a proof. So essentially what we need to say is somehow bound the utility of some strategy in the mechanism by that of truthfulness. And the way we do it is we introduce some auxiliary game in which agents are to satisfy their budgets only in expectation. In this auxiliary game, we demonstrate sensitivity results that goes along the lines of the result I gave you earlier. And then we show that utilities in the auxiliary game and original mechanisms are close. One more comment. So in the bounds that I provided, the number of agents is not in a bound. But what is in a bound is this constant of average payment. And if you think about this, the more agents you have, the less likely they are to win, and hence the smaller their average payment is going to be. And this implicit dependency of number of agents, we argue, is pretty much unavoidable, and we construct a counterexample that shows that for symmetrical agents, this dependency is linear, meaning that loss in welfare and loss in truthfulness is going to scale with n. And this is unavoidable for any mechanism. To summarize, we present a reduction from monetary to non-monetary mechanism. There is a trade-off between objectives of efficiency, incentives, simplicity and tractability. And for a specific case of two agents and instance of monitoring mechanism, we're able to provide a stronger incentive guarantee. Some interesting questions that might be answerable are, is it possible to provide those sorts of POA, price of anarchy guarantees for more general cases than two players? We did not talk about fairness at all, and we feel like some version of approximate fairness for symmetric agents is going to hold, so it might be of interest to provide such guarantees. And finally, the way our mechanism works is it makes a very explicit use of knowledge of a prior, so we need priors not only to set up a budget, but we also need to do the simulating part. And in terms of the algorithm being practical, this is a problem and might be interesting to try to construct mechanisms that do not do the simulation step and thus are less dependent on the precise knowledge of the prior. This is it. Thank you.